So today we're going to be calculating Hess's law for enthalpies of reactions. So up to this point, you've done reaction coordinate diagrams where you could look at a chemical reaction and the progression in a diagram form. We did the same thing for physical changes using a phase change diagram and calculating enthalpies and heat through phase changes. So today we're actually going to calculate delta H for these diagrams. So really digging into this delta H here, which is our final minus initial, because that's what delta means, which just means we're taking the delta H of the products and we're going to subtract that from delta H of the reactants. So that equation is written in this fancy form. Delta H of the whole reaction can be calculated by sigma delta H naught F of the products minus sigma delta H naught F of the reactants. Okay, in essence, delta H of the products minus delta H of the reactants. We have a few mathematical variables we need to define. So first, anytime you see capital sigma, that's going to mean sum of. So sum of all the things after that. So in this case, we are taking the sum of delta H, which you're familiar with, so the change in enthalpy. The naught means standard conditions, just meaning the reference material you're looking up was done in a laboratory under the optimal conditions. F is formation, so the heat of forming that compound, and then products. So a lot of fancy symbols, mostly there to confuse you. Delta H naught of F is still coming on a chart, just like the phase changes we did. So it's the sum of delta H naught F of the products minus the sum of delta H naught F of the reactants. So kind of a scary looking formula, pretty straightforward math though. So a few things, delta H naught F is the heat of formation of a substance. You will always look that up on a reference chart, just like we did for phase changes. This time, however, these reference charts are very ginormous because they are for every compound in existence that we can find a formation heat for. So the last 2 pages of your packet have a standard enthalpy of formation graph for various compounds. These are all metallic compounds or commonly used compounds. The other side of that are ions, which we will not mess with so much in here, but if you need them, they're right there. And the second most important graph are the organic compounds. So you'll see glucose, fructose, those sort of things. On the back side of that, we have our methanes, our propanes, our butanes. Okay, so a lot of combustion material there. So that is where you would get delta H naught of F, is you're just going to look them up. Those charts will be provided to you on a quiz or a test. There is no way anyone expects you to memorize delta H naughts. Rule 2, delta H of an element in its free state, meaning the way it comes in room temperature form, so the way you would find it on the periodic table, including our diatomic elements, is 0. So anytime you see an element, it's going to be 0 in its standard state. Okay, so let's run through an example. In this example, we have the combustion of methane. CH4 plus O2 yields H2O, and this should be CO2 because it's a combustion problem. First thing we want to do is balance that reaction. So 1 carbon in, 1 out, 4 hydrogen in, 2 hydrogen out. So we're going to multiply by 2 here. 2 oxygen in, 2 plus 2 is 4 out. So I need to multiply by 2 here. Reminder that anything blank is just 1, or you could fill in the ones if you wanted to. So looking at this gigantic equation that looks intimidating, we want to know delta H of this reaction. We are going to take the sum of delta H of the products minus the sum of delta H reactants. To expand that out, we are going to take our product. So I need delta H of H2O plus the delta H of CO2. Now, delta H's are always given in kilojoules per mole, right? So on the chart, even in phase diagrams, it's kilojoules per mole. We still have to get rid of the mole part. This time it's a little easier because we have a balanced equation. So you're going to take the coefficient or the number of moles going in or coming out of that reaction and multiply it by your delta H. So I have 2 delta H's for water because I have 2 waters coming out, or twice the energy. Carbon dioxide was only 1, so you could multiply a 1 there if you needed to. All of this is the sigma delta H products. We're going to subtract that from now, the sum of the delta H for our reactants. We're going to do the same thing on the reactant side. I'm going to go find delta H for CH4. I only have 1 mole, so I'm only going to have a 1 there. I'm going to add that to the delta H for O2. Now I have 2 moles of O2, so I'm going to multiply by a 2 there. That is how we can simplify down that equation. Now we're going to go plug in numbers. So 2 times delta H water. So we're going to go to the charts. We're going to go find water. Now we are in liquid water, so we want to make sure we've distinguished which one. It's going to be negative 285.8. I should label my units. So 2 moles times negative 285.8 kilojoules per mole. I'm going to add that to the delta H for CO2. So again, back to the chart, scanning. Most of these charts are in alpha order. So CO2 gas, negative 393.5 kilojoules per mole. Again, we're multiplying that by 1 mole, right? I should throw that on the top. So our mole cancels out, mole cancels out. That is all of the products. I'm going to subtract that from my reactants. So delta H for CH4. So on our chart, CH4, negative 74.8. kilojoules per mole. Again, we only have 1 mole of methane here, so that would be multiplied by 1 to cancel out. And we're going to add that to 2 moles of oxygen. Now, if you go look for oxygen on your chart, it is not here, right? There's no oxygen on the chart. You can look on all these charts. It is not there, and that is because of rule number 2. Elements in the standard state are 0. So oxygen is a gas format. It's a standard state. So it's just 2 times 0. There is no formation of it. That's how it exists. Okay. That is your delta H equation. Now we're just going to go plug that into the calculator. It is imperative that you follow order of operation. So if you're not sure, always do piece by piece. Okay. If you get one thing wrong, it's not going to be pretty. Okay. Here is my calculator work. We end up with negative 890.3. And our units are in kilojoules. So I did 2 times negative 285.8 to get negative 571.6. I added that to the negative 393.5. This whole portion comes out to negative 965.1. I then subtracted that from a negative 74.8 because this just goes to 0. We get our negative 890.3. The final follow-up question is this endo or exothermic? So delta H, very similar to Q. It is negative here, so we have 890 kilojoules flowing out. So this is exothermic. This should make sense because you are combusting methane. So you are literally lighting methane on fire. When things have fire, energy comes out. So we would expect an exothermic reaction here. That is how you calculate Hess's law for enthalpy of reactions. You have the rest of the page to complete on your own.